Welcome to Teach Yourself S1. This is S1 Lesson 5, Probability, Mutually Exclusive and Independent Events. Before you start, it's a good idea to make sure you have a printout of the presentation slides so you can annotate them and perhaps make any additional notes that you may want from the session. And you should definitely at least have a pen, paper and calculator so you can attempt some of these questions and work through with me. So this is an outline of the key S1 topics. We're still on the probability. We're just finishing off now. This will be the concluding topic of probability before moving on to discrete random variables. So what we're going to start with today is mutually exclusive events. Mutually exclusive events cannot occur at the same time. Since the probability of A intersect B equals 0, the addition law then becomes probability of A union B equals the probability of A plus the probability of B. So let's think about this. A mutually exclusive event. Well, a mutually exclusive event is like when you flip a coin. Flipping a head and flipping a tail is mutually exclusive since they can't both happen at the same time. You either have one or the other. Now, if you can either only have one or the other, that means that there's no intersection, there's no overlap, there's no time that both A and B, or heads and tails, can occur. And so that means the addition law goes from probability of A union B equals probability of A plus a probability of B minus a probability of A intersect B. This bit I've just underlined here, that's equal to 0 since there is no intersection, and so we get left with this version of the addition formula. It's worth noting at this point, if you use this version of the addition formula at any other time than with mutually exclusive events, you're going to get it wrong. Personally, I like just working from the Venn diagram. If you see the Venn diagram for the mutually exclusive events, if I want A union B, I'm going to add up everything in A and everything in B and everything in the intersection. So I'd add up everything in A here, everything in B here, and then there's nothing in the intersection to add up. Okay, well, let's look at some examples that will emphasize mutually exclusive events are. So I've got a fair six-sided dice and I roll it. Event A is rolling an even number, event B is rolling a 1. So let's find the probability of A union B. So here's my Venn diagram. We've said that A is even, B is rolling a 1. So let's, rather than putting the probabilities, let's go back to the basics of Venn diagrams here. Let's think about putting the numbers in. So even numbers, 2, 3 hasn't recently become an even number, apologies for that. So 2, 4 and 6. Number 1 goes in here, and then I'm left with the numbers 3 and 5 outside. So the probability of A union B, so the probability of an even number or the number 1 is 1, 2, 3, 4. So 4 out of 6. And that's exactly the same, or 2/3. It's exactly the same as adding a half and 1/6. Okay, so there's a nice starting example to give us an idea of mutually exclusive events and how they work. Let's look at a slightly different one. Given that the events A and B are mutually exclusive and that the probability of A is 0.3 and the probability of A union B is 0.5, we want to find the probability of B. Okay, so what I know is that the probability of A is 0.3. I know the probability of A union B is 0.5. So I mean, really, all I'm looking at is I know that this has to add up with this to give us 0.5. It'll be 0.2. But if we use the formula just for argument's sake, you can see that we get a methodical way to this. As I said previously, I prefer to use Venn diagrams, but we can do it using the formula. So just subtracting 0.3 from both sides, you can see that, as logic would have dictated a moment ago, that we can get a probability of B is 0.2. So I can put the 0.2 in there, and just to be complete, I can fill in the rest of the Venn diagram and then continue on and answer any question based on this scenario. Okay, well, here's one for you to try now. So we've got the probability of A is 0.15, probability of B is 0.45, and the probability of A union B is 0.6. So I want you to determine whether A and B are mutually exclusive. So if you pause the recording now and attempt it before proceeding, and we'll resume in a moment. Okay, so let's go through the answer to this. we had the probability of A equals 0.15, probability of B equals 0.45, probability of A union B was 0.6. I want to show they're mutually exclusive, so if I want to show they're mutually exclusive, what I want to do is I want to show that the probability of A union B is equal to the probability of A plus the probability of B. I want to show that this property here is true. So 0.6 equals 0.15 plus 0.45. Yep, that's true, and it's as simple as that. So there's just a taste of some questions that you may get when doing mutually exclusive event questions. Okay, so independent events. Independent events are such that each one has no effect on the other. So what we mean by this is if you roll a six-sided dice, it has no effect on the result of flipping a two-sided coin. In fact, we can take that a little bit further. If you roll a six-sided dice, it has no effect on the second roll of a six-sided dice, or the third roll of a six-sided dice, or a fourth roll of a six-sided dice. Nothing controls each roll, so they are independent events. If you think about flipping a coin, it doesn't matter what you flip on flip 1, the probability on flip 2 of flipping a head and a tail is still half each. If you was to flip a coin 9 times and get 9 heads in a row, the probability of the next one being a head is still a half, because those 9 previous flips of a coin do not affect the next flip of a coin. You could flip a coin 9,999 times and get 9,999 heads. The probability of the next flip being a head is still 0.5, because those previous 9,999 attempts cannot in any way affect the next probability. So there's some properties of independent events that are really important. We saw in our conditional probability lesson from tree diagrams, we saw a certain property, and it all comes from this idea here. If you have independent events, the probability of A given B is still equal to the probability of A, because the probability of A is unaffected. Or the probability of B given A is equal to the probability of B, because the probability of B is unaffected. Now what we got from the tree diagrams, this was here, this little law here, this was where we multiplied across the branches. We got that the end probability of A intercept B, was equal to the first branch, probability of A, times the second branch, which was the probability of an event B given that A had happened. And so what this means is, when we look at what the probability of B given A is, since they're independent events, actually, we can modify this and we get the probability of A intercept B is equal to the probability of A times the probability of B. Now, this is quite an important law. I'm going to highlight it. But what's more important is the statement underneath it. Just like with mutually exclusive events, this is only true for independent events. If you use this law at any other time, when it's not independent events, then you will be wrong. Okay, the law to use at all times is the addition law. That is always true. And then you have, for mutually exclusive events, probability of A union B equals probability of A plus the probability of B, and that is essentially the OR rule from GCSE. And then the other rule for independent events is probability of A intersect B is equal to probability of A times the probability of B, and this is essentially your AND rule from GCSE. Okay, well, let's have a look at some questions that put this into place. In a game, 2 dice are thrown. Event A is the event that the first dice is a 6. Event B is the second dice is a 6. Find the probability that you get 2 6s. Nice straightforward one, this one. Probability of A intercept B. As I mentioned earlier, probability of rolling dice, each of these different events is independent, so probability of rolling a 6 is 1/6. Multiplied by the probability of rolling another 6, which is 1/6. And so I get a probability of 1 in 36. If you go back to our first lesson on GCSE Essential Knowledge, we found this answer by doing a sample space diagram, writing out something like this. And so by doing a sample space diagram and filling in all these entries, we would have found that there were 36 entries, because there's 6 rows of 6 entries, and only one of them, the top one here, gives you a 6, 6, so 1 out of 36. So this law ties in with stuff we've already seen. Okay, let's look at some slightly different questions. Given that the events A and B are independent, with probability of A equal to 0.15 and a probability of B equal to 0.4, let's find the probability of A union B. Okay, so we've got the probability of A. We were told that that was 0.15. We then got the probability of B. We were told that that is 0.4. And we want to find a probability of A union B. Now, whenever I'm wanting to find a probability of A union B, I'm always thinking that I want to use the addition law. Okay, so here is the addition law. Probability of A union B is a probability of A plus the probability of B minus the probability of A intersect B. Now this is not mutually exclusive events, so this end part here is equal to 0. These are independent events. Now what we've just seen a moment ago is that there is a property for independent events linked to the intersect. And so that property linked to the intersect is that the probability of A intersect B is equal to probability of A times the probability of B, since independent. Okay, now this is only true in this situation because we've been told that they're independent. So we can now write probability of A union B equals probability, let's not put probability of A, let's write in actually here, probability of A which is 0.15. Apologies, not sure what I'm thinking there. Okay, so probability of A which is 0.15, probability of B which is 0.4, and then minus probability of A which is 0.15 times the probability of B which is 0.4. Now you may find in some books they'll give this as a distinct rule. Personally I don't encourage learning it as a separate rule. Just remember the probability that of A intersect B is equal to probability of A times probability of B in this situation, and then use it when necessary to answer problems. But I wouldn't necessarily learn a different rule altogether. So when I put this into a calculator and work through, what we get is an answer of 0.49. Okay, well let's have a look for you to have a go now. So we have two events A and B such that probability of A is 0.2 and probability of B is 0.65. I want you to find probability of A union B, first of all, if A and B are mutually exclusive. Second of all, if A and B are independent. So pause the recording now and attempt the question before proceeding. Okay, let's have a look at the answer to this question. So we was given that the probability of A equals 0.2. I was given that probability of B equals 0.65. A says that they are mutually exclusive, and so there is a particular property that we have for mutually exclusive events, and that's a probability of A union B is a probability that A plus a probability is equal to probability of A plus a probability of B. So we can just simply say probability of A union B equals 0.2 plus 0.65, and it should be as straightforward as that, giving us an answer of 0.85. Okay, part B says that they are independent events. Okay, now what we're saying is part A and part B are completely separate from each other, so part A has no bearing on part B. We're just saying, first of all, they were mutually exclusive, second of all, they were independent events. So we know finding probability of A union B, generally we're using the addition law. Okay, I use the addition law up here, it's just that I'm subtracting 0 because A intersect B was equal to 0. Slight adjustment there, so we know we want to do the probability of A intersect B. Again, what we know is at this point, independent events, probability of A times the probability of B. I suppose up here what I could have done is I could have said probability of A intersect B, and that is equal to 0 for these mutually exclusive events. So we get the probability of A union B is equal to 0.2 plus 0.65 minus 0.2 times 0.65. And so the probability of A union B is equal to 0.2 plus 0.65 minus 0.2 times 0.65 gives us an answer of 0.72. Okay, I hope that all made sense. I hope, more importantly, you got the right answers. Okay, another one for you to try. Two events A and B are such that the probability of A equals 0.4, the probability of A union B is 0.7. I want you to find probability of B, first of all, when they are mutually exclusive, and secondly, when they are independent. So pause the recording now and attempt the question before proceeding. Okay, so let's go through these answers. We've got the probability of A is equal to 0.4. We have the probability of B we are going to be finding, and we have the probability of A union B, which is 0.7. So part A, we're told they're mutually exclusive, so what I know is, just going to save a little bit of space here, probability of A union B is equal to probability of A. I can put in the addition law. I'll tell you what, I will put the addition law in this time, minus probability of A intersect B. So what I know is, in this case, because they're mutually exclusive, probability of A intersect B equals 0. So what I get is that 0.7 equals 0.4 plus the probability of B. So if I subtract 0.4 from both sides, I get that the probability of B equals 0.3. Part B. So in part B, what I know, again, using the addition law, probability of A union B is probability of A plus the probability of B. What we're told in this scenario is that actually these are independent events. So what I know in that case is that probability of A intersect B is equal to probability of A, let's adjust that a second, times the probability of B. Okay, now what actually might help on this scenario, and you'll see why in a moment, is I'm just going to go into change the probability of B to represent the variable x, and you'll see why in a second. So I get the probability of A union B, which is 0.7, equal to probability of A, which is 0.4, plus I'm using x to represent the probability of B, so minus probability of A, which is 0.4, times the probability of B, which is x. Now if I subtract 0.4 from both sides, on the left hand side I get 0.3, on the right hand side I get x minus 0.4x. So I get left with 0.6x. Let's just highlight that little bit there. I'm just doing x minus 0.4x gives me 0.6x. So then solving this equation, dividing by both sides by 0.6, we're going to get probability of B is equal to 0.3 divided by 0.6, which gives you an answer of 0.5. Okay, well I hope that made sense. Let's move on and have a look at some other problems. So, events A and B are such that the probability of A is 0.4, probability of B is 0.5, and the probability of A union B equals 0.7. I want to show that A and B are independent. Okay, so this is a question I know is done consistently badly by lots of students. Okay, it says to show that they are independent, which means you cannot assume they're independent. You are going to have to solve in some way and show conclusively that they're independent. So I've got that the probability of A is 0.4, probability of B is 0.5, and the probability of A union B equals 0.7. So what I want to do is, in order to be independent, and I wouldn't in order to be independent, what I'm trying to do is show probability of A intercept B equals probability of A times the probability of B. I want to show that this is true. So let's first of all find it. Let's find it using the addition law. So probability of A union B equal to probability of A plus the probability of B. Notice in this lesson how often we're using the addition law. It's a really important law to use in conjunction with Venn diagrams. So what we have here is 0.7 equals 0.4 plus 0.5 minus probability of A intercept B. So if I add probability of A intercept B to both sides and I subtract 0.7 from both sides, what we're going to get is probability of A intersect B equals 0.2. So this is definite answer for probability of A intersect B. Okay, it doesn't matter what else happens. I know that this answer must be true because the addition law is true for all situations. Now, what I'm trying to do is I want to show that probability of A intercept B is probability of A times probability of B. So let's see if that's true. So this is what we're trying to show is true. So is 0.2 equal to 0.4 times 0.5? Well, yes it is. Therefore, A and B are independent. And please remember, in a question where you're asked to show something, you must state your result. There is an answer mark then for this last line of your answer. And if you don't give it, then you lose a mark. Okay, so that doesn't matter how well you've answered the rest. If you don't state what you found, you lose a mark at the end there. Okay, time for you to try one out. So, events A and B are such that probability of A is 0.35, probability of B is 0.4, and the probability of A union B is 0.6. I want you to determine whether they are in A and B are independent. So pause the recording now and attempt the question before proceeding. Okay, so let's look at some answers. We had probability of A equals 0.35, had the probability of B is equal to 0.4, and we have the probability of A union B is equal to 0.6. So I want to determine whether they're independent or not. So, in other words, very similar to the question where we had a moment ago, find probability of A intersect B equals probability of A times the probability of B. I want to find out if this is true. It's just the same question as before, just slightly reworded. Okay, so let's use the addition law exactly as I did a moment ago in order to find what the probability of A intercept B is. And then I can check to see whether the property for independent events is true. So we get 0.6 equal to 0.35 plus 0.4 minus probability of A intercept B. So we're going to subtract 0.6 from both sides and we're going to add probability of A intercept B to both sides. So I get the probability of A intercept B equals 0.75 take away 0.6 is 0.15. So now let's do probability of A intercept B equal to probability of A times the probability of B. And so we get 0.15. Is it equal to 0.35 times 0.4? And the answer is no, they are not equal. So I wouldn't necessarily write this bit in, but if you do 0.35 times 0.4, you're going to get an answer of 0.14. So what I have found out, since probability of A intercept B is not equal to probability of A times probability of B, probability of A, therefore A and B, are not independent. And again, if you don't write this concluding line, you'll lose a mark from the mark scheme. Okay, I hope that made sense, and I hope, more importantly, you got the right answer for that. So I think just have a couple more to have a look at, and then we'll conclude the lesson. So this is going to be a particular type of question now that comes up. So we've got Alan and Bill. They play a game of darts in which they throw a dart and a ball on the dartboard. Alternatively, starting with Alan, and the winner is the first to hit the ball. Each time they throw a dart at the ball, Alan hits with a probability of 0.2, and Bill hits with a probability of 0.3. We want to find a probability that Bill wins the game on his first throw. Okay, so what we're saying is that probability of Alan hitting the ball is 0.2. So let's say A equals 0.2, and probability of Bill hitting the ball is 0.3. So this is an example of independent events, because whether Alan or not hits the ball, what Alan does doesn't affect what Bill does. So each one of these darts throws is independent. So the probability, first of all, probability Bill wins first. Well, what's going to happen here? Well, what's going to happen is we've got to have probability Alan misses and Bill hits. So I'm using A complement there for A equals, let's make sure this is clear, Alan hits. So A complement is that he misses, B is Bill hits. Okay, so probability of A complement intercept B. Now these are independent events. So A complement, if you need to do, perhaps write these on the side as well, is just what adds up to 1. Probability of B complement, we may need later, is going to be 0.7. Okay, so probability that Bill wins on his first throw is 0.8 times 0.3, which is 0.24. Part B says find the probability Bill wins with his second throw. Okay, so this is going to be, and let's think about how this happens. First of all, Alan's got to miss, then Bill's got to miss, then Alan's going to miss, and Bill's going to miss. Bill's going to hit, sorry. So what we get as an answer for this is I get 0.8 times 0.7 times 0.8 times 0.3. And so when we do this on a calculator, we get an answer of 0.1344. Part C says find a probability that Bill wins the game. Now this is an important part, and this will be worth lots of marks in the exam. What we have to identify here is that what's happening is that the probability that Bill wins first is 0.24. Let's put B1 for probability of Bill wins first. That's 0.24. And then probability of Bill wins on his second one. Well, let's just underline these two parts. I'm going to highlight this 0.24. This matches up in the probability of Bill winning second in this part of our probability. And in the probability of a round where both miss is highlighted in red. So what I get is, I get the 0.24, which is the round where Bill wins, times by 1 round of both people losing. So this is the red part. And then that gave me my answer. And then if I look at probability Bill wins third, I get probability of winning a round where Bill wins. So that's the last thing that happens, but we know it's going to happen. One round where Alan misses and Bill wins. We're going to have to multiply this by not just one round of them both missing, but 2 rounds of them both missing. So what I'm going to get is times 0.56 squared for 2 rounds. And I'll do one last one just to emphasize and explain the point. Probability Bill wins round 4 is 0.24, because there's going to be a round in which Alan misses and Bill hits, and then 3 rounds of them both missing, which is 0.56 cubed. So just again colour coding, this is a round of them both missing, and this is a round where Alan misses and Bill hits. Well, this forms a geometric series. Okay, so I mean, when we look at these, probability of Bill winning, is a probability that he wins in the first round, or probability he wins the second round, or probability he wins the third round, or, and this can keep on going forever. And so what this is this is the probability of, this is found because these are all mutually exclusive events, that only one thing can happen or the other. This is found by actually doing the probability of Bill winning round 1 plus the probability of Bill winning round 2 plus the probability of Bill winning round 3 plus probability of Bill winning an infinite round. Okay, and this is a geometric series. It's a geometric series where the first term A equals 0.24 and R, the common ratio, equals 0.56, because each round, where both miss, the probability of that happening is 0.56. So we had, in the first round, there was no round where people both miss. For a second round, we had to both miss once. In the third round, we had to both miss twice. In the fourth round, we had to both miss 4 times. So what I've got is this geometric series situation. So if I find the sum to infinity, because I want to add up all the probabilities of winning either in the first, second, third, fourth, right up to the infinite round, then what I can do is I can use the formula for the sum to infinity to calculate the probability of Bill winning. And so probability of Bill winning is going to be A, which is 0.24, over 1 minus the common ratio, which I've identified as 0.56. And so when we work through this on a calculator, we get an answer of 6 over 11. Okay, now this is a particular type of question. Yes, it's more complex. You'll have to learn to identify when you have this type of question. Okay, now I hope that made sense, because there's one for you to try now. Okay, so Cassie and Daisy take turns trying to throw coins into a pot, starting with Casey. Each coin thrown, the probability that Casey is successful is 0.1 and that Daisy is successful is 0.2. So we want to find the probability that Daisy wins with her first row. We want to find the probability that she wins with her second row, and we want to find the probability that she wins. So what I want you to do now is to pause the recording now and attempt the question before you proceed. Okay, so let's have a look at this question. Again, I'm going to use the space as much as possible. We're going to have probability C, that's Casey getting it into the pot, that's 0.1. So probability of her missing, which is going to be useful in a second, is 0.9. And then we're going to have probability that Daisy gets it in the pot will be 0.2. And the probability that she misses is going to be 0.8. So part A, probability Daisy wins first. It's going to be a probability of Casey missing intersect Daisy hitting. So we're going to get 0.9 times 0.2, since these are independent events, which is 0.18. Probability Daisy wins second. Well, that's going to be probability Casey misses, and Daisy misses, and Casey misses, and Daisy hits. So I get 0.9 times 0.8 times by 0.9 times 0.2, and so when we calculate this answer, we get an answer of 0.1296. Now, the probability that Daisy wins is again going to be probability of D1 plus probability of D2 plus a probability of D3 plus dot 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 plus the probability of D infinity. Now, as soon as you identify that you've got this situation where you can't identify what round she's going to win, it could be an infinite amount of times that they do this, you know you're going to do these types of series. And we know D1 was what D1 is. D1 is 0.18. We know what D2 is. So what we need to notice is, in our probabilities, around where Cassie misses and Daisy hits, I've highlighted, is that 0.18, and around where both miss is this 0.9 times 0.8. So just again thinking about it intuitively, just to explain it for you, probability D3 would be around where they miss, 0.9 times 0.8, twice, so that's 2 rounds, times by 0.2, let's do 0.9 times 0.2, let's follow that order, times 0.2. Okay, and so I can highlight these just to emphasize where they link up. That's around where they both miss. This is around where Cassie misses and Daisy hits, and so this is calculated by 0.72 squared times 0.18. So what we have again is this infinite series. It's a geometric series where the first term is 0.18 and then the common ratio is 0.72. So don't need to go through all of these. This is just D3 is just to emphasize the parts of the formula that we need. The common ratio is identified by the probability of around where they both miss, because that's the one that's going to repeatedly happen, and the first term is the probability of Casey missing and Daisy hitting. So now all we have to do, remember the sum to infinity of any geometric series is a over 1 minus r, so the probability that Daisy wins can be found by doing a, which is 0.18, over 1 minus r, which is 0.72, and so we get an answer of 9 over 14. Okay, well I hope that made sense, and more importantly that you managed to get that right. So that concludes the mutually exclusive and independent events topic and the probability topic. At this point you should do the mutually exclusive and independent events exercise, practice it until you feel confident and that you feel that you can attempt anything. And then once you've done that, if you attempt assessment 5 and bring that into our workshop. Okay, hope that all made sense. Please feel free to drop in and ask questions.